The MIG YouTube channel. Today, we'll be talking about fractals. Fractals are defined as a curve or geometric figure in which each smaller part has the same statistical character as the whole. Take the Sierpinski triangle for example. This one was made in PowerPoint, so it doesn't go on forever, but the pattern will repeat infinitely in an actual Sierpinski triangle. Another well-known fractal is the Mandelbrot set. Discovered by Benoit Mandelbrot in 1978, the Mandelbrot set follows a relatively simple equation. It's a set of all complex numbers c in the complex plane where the absolute value of z is bounded for all positive n and z0 is equal to 0. This fractal would be important for chaos theory. Now, let me pass my time on to Xavier.
Explain the mathematical principle behind a fractal. So a fractal is a complex pattern that exhibits self-similarity across different arbitrarily small scales. So what is self-similarity? It is basically a property of an object where no matter how much the object is scaled, this object will still have the same repeating pattern. So in the bottom right corner, I have a GIF of the Mandelbrot set, which does also exhibit self-similarity because it is also a fractal. When you zoom it in, you scale it, you will see that the Mandelbrot set exhibits self-similarity. Generally generate a fractal. So you would normally start off with a starting shape, a point, or even a number on a plane of the complex plane. Then you repeat a sequence of steps infinitely many times. And each repeated sequence of steps is what we call an iteration. And this is done in an ongoing feedback loop that repeats infinitely many times. And after infinitely many iterations, you will end up with your fractal. So this may not sound very clear. After all, I'm just explaining it in words. So we will now demonstrate how we can create a fractal by using one of the most classic examples of what a fractal, a Koch snowflake.
So how can we create fractals? First, let's start with an equilateral triangle. What we want to do is iteratively make operations on this triangle, which, after making them on and on and on, we get the final fractal, called the Koch snowflake. First, take one of the sides and subdivide it into 3. Then, we want to make this red thing into a bump, like this. We do this for every single one of the sides to get this 6-pointed star. And now we continue doing this operation. Look at each of these smaller sides now, and do the same kind of bump. So we get this more pointed figure. Continuing this on and on, we get the final thing called the Koch snowflake, and this is how we create this fractal. Other fractals can also be created in this same kind of iterative way. Just keep on applying the same operation and we get this infinitely nested structure.
Now here we have some real-world examples of fractals. It turns out that the self-similarity of fractals can be seen quite widely in nature or in real life. For example, fractal landscapes. In Guardians of the Galaxy Volume 2, there's been fractals used a lot to make some quite realistic imagery or quite intricate detail. For example, these two scenes right here. Or in fractal cities, here the self-similarity of fractals are exploited to make quite some intricate detail in these fractal cities. These are used quite widely in computer graphics and CGI to make quite detailed scenes. Next, we have fractals in nature. For example, in broccoli or cauliflower, these leaves can be seen to be quite self-similar and equate some intricate patterns that resemble fractals. Or another example is genome structure like fractal globules. Turns out that some genomes in our body look like fractals, and these can help us in understanding our body better. Furthermore, we have fractals in medical imaging. For example, lung tissue or blood vessels quite look like fractals due to their self-similar nature as well. And by analyzing these fractals, we can possibly detect some diseases early, such as cancer. Well, that's it for this video. Thanks for watching.